All right, so in this video, we're going to be looking at some variation problems. We have examples with both y varying directly and also y varying indirectly. And then we have a third example that's a little bit more complicated to set up the equation, but we're only going to set up the equation. Now, in the first two examples, these are going to follow a typical pattern for variation problems. You get some explanation about how the variables are related to each other. Then you get some values where we know what the variables in both cases or all three cases are doing in order to find our unknown scaling factor. And then we're asked to find one of the variables when the other variables in the equation are known. So we're going to start with y varying directly as x. So in our first example, this is the simplest possible scenario. Y varies directly as x. So y is some scaling multiple times x. Now, we know in this particular example that when y is 45, x is 5. So that's going to mean that we can solve for that scaling factor, the constant of variation. 45 divided by 5 is 9. And so our equation of the direct variation is going to be y equals 9x. And then all we need to do from this point to finish the problem is to find y when x is 13. And so we will use our constant that we found times the value of x that we were given. 9 times 13 is 117. Most problems involving variation problems like this are going to follow the same pattern. So let's look at our second example. Y varies directly as x. It's going to start out the same way. And inversely as the square of z. So when it says inversely, that means it goes into the denominator and it's z squared, not square root. Sometimes students will read these too quickly and they will get a problem confused with one is a square, maybe another one is a square root, and switch them. Put into the equation exactly what is written there. If it says square, then it's z squared. And if it says square root, then it's the square root. And don't miss the word root or try to switch them back and forth. Now, as with the previous example, we are given some information. Y is 20. We don't know what k is yet when x is 100 and z is 5. So this is going to simplify to 100k over 25. And 100 divided by 25 is 4. And so if I divide by 4, on both sides, I get k is equal to 5. So it's now 5x divided by z squared. And then I'll be given information. I want to evaluate y at some value of x and z. Find y when x is 9 and z is 3. So y is equal to 5 times 9 divided by 3 squared. I'm going to get 5 because 3 squared is 9. The 9s are going to cancel, and I'm just left with 5. Now, the final example, and I'll recopy it so we can stare at it a little bit more carefully. Now, this one is not a full problem. It's just a set up the equation kind of thing. We have x varies directly as z and inversely as the difference between y and w. Now, whenever you see sum or difference or something like that, they mean for you to do that operation first and then do the inverse part. So here, the difference goes in the denominator. Both parts go into the denominator. If this was inversely as the sum of y and w, then it would be y plus w. Or it could say inversely as the product of y and w, in which case it would be y times w in the denominator. So there are these sum difference quotient type things. They can apply sometimes in these problems, and you do kind of have to keep in mind your order of operations. Different sum product, as they essentially act like parentheses terms. They tell you what operation and they say do these before you do the other things that you need to do with it. So we're inversely related to the difference. So we do the difference first and then we put the difference here in the denominator. If we had other information, we would proceed with solving this exactly the same way as we did with the others. We would need values for all 4 of our variables in order to find k. And then typically they would ask, here's 3 values, find the one that's missing, that's left.